Hello, welcome to my final presentation for the Mechanical Behavior Materials project. The project title is Structural and Thermal Analysis of Automotive Disc Brake Rotor. This is a quick recap of the project that I've been working on. The disc brake is a device for slowing or stopping the rotation of a wheel. Repetitive braking of the vehicle leads to heat generation during each braking event. Steady state thermal and static structural analysis of the disc brake rotor is aimed at evaluating the performance of the disc brake of the car under severe braking conditions, thereby assisting in the design of the rotor. The analysis was carried out for a ventilated disc brake with different materials, and the results were compared, thereby allowing for the selection of the optimal material. This is a quick look at the geometry of my disc brake that I've used. As you can see over here, that it is a ventilated disc brake. It is made up of two discs which are joined by these vents right over here. It's also provided with circular and slot vents along the braking face for heat dissipation. The CAD modeling for this disc brake was done on SolidWorks, and so was the rendering that you see over here. This is an engineering drawing to give you a further look at the geometry of the disc brake that I've used. As you can see over here, the outer diameter of the disc brake is 180 mm and the inner diameter is 104 mm, and together this area over here forms the braking face of the disc brake rotor. As you can see that the disc brake is made up of two plates, 5 mm each, and the total thickness is 15 mm for the disc brake. This is a project schematic or the flow of the ANSYS workbench analysis that I've used for the disc brake. You can see on the left hand side is the steady state thermal module of ANSYS workbench. The CAD model was initially uploaded onto this module, and a temperature was applied on the disc brake followed by convection, and the results that were obtained were plugged into the static structural analysis module of the ANSYS workbench. Over here the disc brake rotor was fixed and braking force was applied, thereby deriving the deformation and the stress contours. Now, the materials that I've considered for this analysis are the materials which are commonly used for manufacturing disc brakes in the real world. These materials include stainless steel, titanium alloy, cast iron, and aluminum alloy. These materials were selected to keep the results as close to real world conditions as possible. Moving on. These are the analysis settings or the boundary conditions that were applied in the workbench analysis. Over here, the temperature that I applied was 500 degrees Celsius, and this temperature was applied on the faces, which you can see on the left hand side in red. Now, the mass of the vehicle was considered to be 1385 kgs. The time required, or the braking time of the vehicle, was 45 seconds, and the effective diameter of the brake pad, which is again the external diameter of the disc brake that I've used, was 180 mm. The formula used for deriving the braking force is the formula given over here. Once I plugged in all the values, I derived the braking force to be around 1047.36 newtons. But for the sake of simplicity, I applied a braking force of 1050 newtons, and this was again applied on the face shown over here in red. The right hand side image shows you the faces of convection of the disc brake, which were given in yellow. Moving on, this is the mesh that I derived in the workbench. As you can see over here, it's a fine mesh, and the mesh is much more defined along the vents provided over here, and it's quite equally spaced along the hub. The right hand side image gives you an idea of the number of nodes and elements that I had. As it is apparent, I had around 3 million elements. Moving on, these are the deformation and stress contours that are derived from my steady state thermal and static structural analysis. As you can see over here, these are the contours for stainless steel. On the left hand side, you can see the deformation contours, and on the right hand side, you can see the stress contours. Now, it is apparent from these contours that the deformation is mostly isolated along the outer edges and it keeps reducing till it gets to the hub, whereas it's the opposite for stresses. The stresses are highest at the hub, which are where the disc brake will be attached to the wheel, and it goes on decreasing along the outer edge. Moving on, these are the deformation and stress contours for cast iron. As you can see over here, the maximum deformation and the maximum stress for cast iron is actually much lesser than that for stainless steel. This trend continues for titanium alloy. These are contours for titanium alloy. As you can see, there is a considerable decrease in the maximum deformation derived and also the maximum stress which is derived under the same boundary conditions. These are the deformation and stress contours for aluminum alloy. Over here, there's actually an increase in the maximum deformation and the maximum stress which would derive, but when compared to titanium alloy. But when these results are compared to cast iron and stainless steel, these are actually still less. This is a quick comparison of the deformation and stresses that are derived from my initial analysis. As you can see over here, the deformation is least for titanium alloy, followed by cast iron, followed by stainless steel, and it's the highest for aluminum alloy. And for the stresses, we see a slightly different trend. Again, it's the least for titanium alloy, followed by cast iron, aluminum, and it's the highest for stainless steel. So from the above comparison, it is inferred that titanium alloy would be the suitable material for manufacturing these disc brakes, as it has the least deformation and stress induced based on the thermal and structural analysis. Moving on, these are the factor of safety contours for different materials. As you can see on the left, we have the factor of safety contour for stainless steel. Over here, the highest factor of safety we derived is 15, which is along the outer edge, which is where the stresses were the least. And it's the least, which is around 0.04 along the hub of the disc brake, where the stresses were highest. Now, since the minimum factor of safety is around 0.04, this material cannot be used. It would be unwise to use this material for manufacturing this brake, because whenever a mechanical component is designed, generally the minimum factor of safety that is aimed for is around 1 to 1.2. On the right hand side is the factor of safety for grey cast iron. As you can see, it's failing all over, thus by ruling it out in our manufacturing of the disc brake. Now, these are the factor of safety contours for titanium alloy and aluminum alloy. So, the factor of safety contour for titanium alloy further backs our claim that titanium alloy would be a good material for designing this disc brake, because as you can see over here, the maximum factor of safety is again 15, which is along the outer edge. But what you will notice over here is, even though it says that the minimum factor of safety is around 0.7, these areas are actually isolated along the holes which are used for bolting on the disc brake onto the wheel. You can see the minimum average actually is around between 1 to 5 over here in the yellow area. So we can say that the design is actually safe, and titanium would be an excellent material for usage in a disc brake. The right hand side image shows you the factor of safety contour for aluminum alloy. Over here it can be seen again that the maximum is 15, which is along the outer edge. But an interesting part over here is, even though it says that the minimum is around 0.12, which is along the hub, the area where the factor of safety is actually pretty less is shrunk compared to over here, as you can see, for stainless steel and grey cast iron. So based on this, it can be inferred that aluminum alloy would actually be a good backup material to titanium alloy in case cost is a hindrance, because the only hindrance in selecting titanium alloy as a material that can be used for disc brake is the cost, since the market value of titanium alloy is really high. Moving on to the second part of my analysis, this is the fatigue tool results. So the fatigue tool option in Access Workbench was used to evaluate the life of the material and also the damage that would be induced in the material due to cyclical loading. The fatigue tool gives a good idea about the crack propagation in the disc brake, which is the location where the crack propagation might start for a particular material, and can help with determining the areas that can be strengthened further to improve the proposed design. Now, for using the fatigue tool in ANSYS Workbench, the SN curves for some of the materials had to be defined, as they were not defined for all the materials that were selected for the analysis. This is a quick look at the various SN curves for the selected materials. We'll be starting from the left, which is stainless steel, and moving counterclockwise. Moving clockwise, we have the SN curve for iron, cast iron, aluminum alloy, and lastly for titanium alloy. As you can see over here, in an SN curve, the S stands for stress and the N stands for the number of cycles. So the number of cycles for which the stress is applied. The SN curve gives you the fatigue limit of a material, beyond which crack propagation would start due to the cyclical loading. Now, using the fatigue tool in ANSYS Workbench, we derive the life and damage contours for the different materials. Starting with stainless steel, you can see on the left, this is the life expectancy contour for stainless steel. You can see again that the life expectancy is the least where the stress was the highest in the stress contours, which is the internal hub, and it's the highest for the external edges. A similar trend is followed by the damaged contours. The damage is highest at the hub, followed by and keeps on reducing till the edge. This is again followed for cast iron. You can see over here damage is highest for the hub and it's the least for the external edges, keeping in line with stress contours. And similarly, it's the same behavior for the damage contours. Now, these are the most promising results that I got using my fatigue tool. As you can see over here, these are the life expectancy and the damage induced contours for titanium alloy. You can see over here that the life expectancy is pretty good for titanium alloy throughout, except for along the wheels, the holes of the hub where the disc brake would be bolted onto the wheel. But you can see over here that these are pretty isolated results, which can be due to stress concentration. So overall, you can say that the life expectancy for titanium alloy is pretty good, and the damage induced is pretty less. Now, these are the life expectancy and damage contours for aluminum alloy. As you can see over here, even though the life expectancy is not the greatest for aluminum alloy along the outer edges, the life expectancy is pretty good along the hub when compared to stainless steel and cast iron, and thus overall aluminum alloy is a good backup material to titanium alloy, as we inferred earlier. The same can be seen for the damaged contours. The damaged area is actually shrunk. Now this is the crack propagation I was telling you about. So from the damaged contours, we can actually see the area where the crack propagation might take place. As you can see over here, it's along the holes. So this fatigue cracking, though quite small initially, can cause significant damage over time, and thus further strengthening can be done in these regions if the proposed design was to be improved and to increase the life, because good fatigue performance is the most important factor for cyclically loaded components like disc brakes to ensure long-term reliability. So in conclusion, just a quick recap. Based on the initial analysis, we found out that aluminum alloy would be the ideal material, but its selection could be a problem because of the high cost of the material. A viable option for titanium alloy would be aluminum alloy. While the deformation and stresses generated in aluminum alloy are quite higher to titanium, the results are still better compared to stainless steel and cast iron. The fatigue tool analysis shows a similar trend where titanium has the highest life expectancy and the least damage induced in the body of the disc brake, followed by aluminum alloy. The fatigue tool gives a good idea of the location of the crack propagation in the disc brake, and the propagation would start at the hub, specifically the holes provided for bolting the disc brake, and thus this area can be strengthened further in case the design has to be improved. Thus, the results derived, if cost is not a barrier, I would say that the ideal candidate for the disc brakes would be the titanium alloy, and the economical alternative to titanium alloy would be aluminum alloy. So this has been a presentation of my final project. Thank you for watching.